Hello, good morning, good afternoon, or even good evening, depending on where you are in the world today. And welcome back. It is 2026, and this is our first webinar of the year. So we hope you all are surviving winter in the Northern Hemisphere or Southern Hemisphere summers, and back to work and fit and healthy, ready to go. Today, for the first webinar of the year, I am actually excited, Lars, Kevin, I hope you live up to that, that today we are introducing to you a new material, a higher thermal class conductor insulation paper, not to be confused with current Weidmann products, so thermally upgraded materials, or DPE paper, which is designed as an engineered paper specifically for distribution applications. This, for the first time, is a higher thermal class conductor material that is targeting the power sector of our market. So an interesting topic, a new topic. So I will not spend too long introducing, but just the usual reminders. I will be back at the end to ask both Lars Dreyer, our head of laboratories, testing, research and development in Rapperswil, Switzerland, Kevin Biggie, our head of technology and innovation for the Americas region, all of your questions that you put in the chat box, or as many as at least we can get to. Also, thanks for your questions in advance. Once again, yes, the presentation will be made available afterwards. You will receive an email with both the link to the recording of the webinar and also to the slides themselves. So yes, you will have those at some point in the next 24 to 48 hours after the webinar. And if you have questions in the webinar, whenever you're ready, you hit the question mark button, fill your question in. Don't worry, you won't disturb Lars and Kevin. Only I see those. So we will try our best to get to them at the end. So with that said, I will hand over to our team. Kevin, I believe you will kick us off this morning here on the East Coast of the US. So thanks very much, and I will see you all at the end. Thanks. Over to you, Kevin.
Great. Thank you very much, Frankie. I appreciate the introduction. And so again, I'm Kevin Biggie, and so today I'm really excited to talk to you about a new innovation that we have. Again, Frankie already mentioned it, but yes, it is a new conductor insulation paper with a higher thermal class, specifically for power transformers. And when we talk about the higher thermal class, it says there that it's 130 degrees C in mineral oil. So we're going to talk all about that and how it relates to current insulation and the benefits that thermal class provides. So today, Lars and I are going to talk really in two sections, and then the third section will be for open discussion and Q&A. So I'm going to start with a little background and theoretical overview. I'm going to talk about overloading, and I'm going to talk about temperature limits and how this new conductor insulation paper can overcome temperature limits of standard thermally upgraded papers currently. So just as a kind of a very basic background, today we're talking about solid insulation for power transformers, so bigger power transformers. So the solid insulation and transformers are really what define the major characteristics of a transformer. So the solid insulation affects how big the size and weight of a transformer is. It defines losses and efficiency, and ultimately the lifetime of the transformer is dependent on the solid insulation. So the solid insulation is performing three main functions. So the first of all, it's performing the function of an electrical insulation. So cellulose-based solid insulation materials, papers and boards, together with dielectric liquids, are an excellent insulation system. And especially dried cellulose with impregnated liquids are very well known in the industry and have been used for a very long time, over 100 years. It also provides mechanical support. So these transformers are subject to certain forces. So you need a strong material in order to hold the transformer windings together. And again, cellulose press board and paper provide excellent mechanical stability to the windings. And finally, the insulation system performs a cooling or heat transfer function. So the solid insulation material is porous and it impregnates with the liquid. And so the liquid can move through the material and in and around it. And so this insulation system is also great for heat transfer purposes. So to go from solid insulation generally to the topic for today, we're going to be talking specifically about what's called conductor wrap insulation. So you can see the picture in the upper right there is a photo of a conductor wire that is being wrapped with many layers of electrical grade paper. And so again, the purpose of that electrical grade paper wrapped around the wires is to prevent current from flowing between those wires in a winding. And there's two main types of such conductor insulation. So the first type is a calendared crepe paper. So our Weidmann 22HCC brand is kind of a gold standard of a calendared crepe paper for wire wrapping, which has very, very high strength and flexibility. And it's excellent for wrapping around wires and also for use when winding the coil in a transformer. And then there are also just standard flat papers used in this application as well. Some design considerations for wire wrapping papers is that the total thickness that are wrapped around the wires are used, based around the turn-to-turn voltages in the windings. And our calendar crepe papers, like HCC papers, they wrap very, very tightly to the wires and provide excellent turn-to-turn voltage protection. And then the other thing that's important to the design of the other important consideration for these papers is that they have temperature limits. So depending upon which type of paper you use defines ultimately the temperature limits for the transformers. And there are standards that define the temperature limits for transformers based on which thermal class insulation paper you use. Okay, so now we're going to move on to loading. So and how the conductor wrap paper affects temperature limits based on loading. So during normal loading conditions, there are low temperatures. There are loading guides in both IEC and IEEE that apply that set temperature limits during normal load conditions. And you don't really need high temperature capable insulation materials for normal loading. However, under overload conditions, losses increase, and from that the temperatures increase. And so if a transformer experiences regular sustained overloads, those higher temperatures from the higher losses can actually degrade the insulation. And in power transformers, the wire wrap paper is a key insulation product that degrades first because it's right next to the conductors. So there are standards that set temperature limits in order to avoid significant loss of life of the solid insulation and the wire wrap paper in particular. There are other standards that cover the use of higher temperature insulation materials, and we're going to talk about that too. But if higher temperature capable materials are available, what they do is they allow to have a lower loss of life of the wire wrap paper during overloads. Or you can withstand higher overload temperatures with the same loss of life. And ultimately, the benefit that provides is you actually need fewer transformers on the grid, because if you design the grid for typical N-1 reasons, which is mean you have backup transformers to be able to shift load to if a transformer goes out, having a higher temperature capable paper will allow higher temperatures in that overloaded transformer without a significant loss of life. And so you'll need fewer transformers, which means you can ultimately increase the short time overload limits for temperatures with higher, for transformers rather, with higher thermal class papers, which means you can free up capacity for new load and generation. You can reduce your investment needs and ultimately provide backup capacity in case of emergencies. Okay. So I mentioned that there are standards that cover the use of higher temperature insulation materials. And one example is the IEC standard 60076 part 14, which covers the use of high temperature insulation materials in liquid immersed transformers. So, so the chart on the right, shows different levels of the use of high temperature insulation materials and kind of the different combinations. So in the left-hand column, the conventional insulation system there is referring to non-thermally upgraded paper and mineral oil. Okay, and then the next column to that, the semi-hybrid winding, is the use of thermally upgraded paper. And thermally upgraded paper, thermally upgraded craft in mineral oil is 120 degrees C thermal class system. So this new paper that we've developed is actually 130 degrees C in mineral oil. And the semi-hybrid winding does not use high temperature spacer material. And then a mixed hybrid says that you can use one or the other. And so this new paper we've come up with achieves a 130 thermal class without the need for any different spacer materials. Just the new conductor paper alone will allow 130 degrees C. Now this chart in the standard also has a sister standard, so to speak, in the IEEE world, which is called IEEE C57154. Now, getting to the spacer material. So, the traditional, or I'd say older view is that the cellulose press board is somehow limited in thermal class to 105 C. And I just want to mention that we actually did a special study and wrote a technical paper, which is described in the slide, that shows that actually standard cellulose press board in the system with thermally upgraded paper and mineral oil is actually 120 C thermal class. So, so again, standard cellulose board, thermally upgraded craft and mineral oil, that system is 120 degrees C. You can look for details in this technical paper if you're interested. And so therefore we feel that we don't need special spacer material in order to use this new conductor wrap we've come up with 130 degrees thermal class capability. So what we're saying here is if you go further into the IEC 60076 part 14, so what we're talking about is this kind of arrangement shown in this figure here, where the only difference, okay, is a higher temperature conductor insulation, right? That's what's called a semi-hybrid winding in this standard and according to this figure. But instead of the 120, which is meant to represent thermally upgraded craft, with our new paper, we're actually achieving 130. So you can get that 130 again without new spacer material. So what does that do? I want to highlight these three rows here because they talk about the hot spot. Okay, so what this means is that the use of this new paper will allow 10 extra degrees hot spot temperature under normal load, and then it'll allow 10 additional degrees under long-term overload, and then 10 additional degrees under short-term emergency overload. So this these are the new thermal limits by using this paper, are these extra 10 degrees. 10 degrees under normal load, long-term overload, and emergency short-term overload. And that's what is the benefit of this paper, are those extra 10 degrees. Just to mention quickly about efficiency, right? So transformer efficiency is based on, really it's based on losses. It's based on both no load and load losses. No load losses coming from the core, load losses coming from the winding. And you know, there's the equation, one example equation of an efficiency calculated from the EU Eco Design Standard. But during overloading, you know, these efficiency you know, limits aren't valid anymore, because overloads are just a short-term thing. Now, to talk about an example of real-world overloads. So this is a picture from the website of a utility in Europe, and it's basically showing an example month of June of the photovoltaic, you know, when the sun comes out in the summertime, hitting the grid. And so you can see that there are, you know, daily peaks from photovoltaic infeed that affect transformers. So every day you're getting the possibility of an overload, daily overloads. And so and the very, you know, bottom picture is just showing an example peak from one particular day. So one thing that this conductor wrap insulation paper you can benefit from is specifically the effects of overloads from renewable energy, you know, which often you know, is not a constant load, but it's changing in a very big way on a even daily basis. So so that's the background, and then I will turn the microphone over to Lars, who will actually tell you a little bit more about this new paper itself. So Lars, please go ahead.
Thank you, Kevin. So what are current high temperature solutions right now? We have the so-called meta-aramide materials. You have a picture on the left side of these materials. This is a high temperature material going up to 180 degrees or even 220 degrees, and you see that Weidmann, for example, can do most of the products that we usually produce with cellulose-based materials also in meta-aramide. Another solution is a hybrid material between meta-aramide and cellulose. It's mostly used for manufacturing papers, where you have a paper with the core made from cellulose paper, and then the outer layers are done by a meta-aramide. We have other materials usually not used in liquid filled transformers, like for example mica, or there are other organic or inorganic materials, blends with cellulose or whatever. Most of them not used for liquid filled transformers. And last but not least, we have our Weidmann DPE paper for distribution transformers, a paper which is has a thermal class of 130 degrees. We released this paper to the market about 7 to 10 years ago. Next slide. What was the trigger to start this development project for inventing a new paper for the use of wrapping conductors in power transformers? As I said, we had already the DPE as a 130-degree thermal class paper in mineral oil for distribution transformers. And due to this, we got also interest from the market to use this or a similar paper or product for the application in power transformer. So this was really the initial trigger to start a project. One very important thing for the validation of such a paper or such a thermal class for a material is to execute an aging test. Next slide. Executing aging tests is an extremely resource demanding task. So you need a lot of time, you need manpower, you need equipment, because you have to do the aging in a matrix. So at least 3 different temperatures are usually performed. And for these 3 temperatures, you have to measure different times. And this is now an example in the table for such a matrix. The longest time here is 4,000 hours, which is roughly about half a year. Most of the time, you cannot really calculate the end time that exactly, so you have to usually calculate with more time. So to seriously make or perform an aging test, that takes at least 1.5 to 2 years. Next slide. Executing an aging test, there are very important factors that can influence the result. Depending on the aging vessel you use, you can have different parameters or conditions within the aging vessel that have then an impact of the aging of the material. You can have different temperatures that you select. You have to evaluate one of the properties that you can determine the aging property of the paper, for example. So there are different parameters to test. You can either do degree of polymerization when it's a cellulosic paper. You can measure tensile strength or elongation or any other mechanical property that gives you a hint or a measure for the aging status of the paper. The ratio solid to liquid insulation is all very important, and it is also specified then in the standard. You don't really get a temperature class, but you can calculate the temperature class, but this is always based on an industry proven system or on a reference system. And depending where you're living, the standard or the reference system is different. In IC world, the reference system is a standard kraft paper. And in the IEEE world, a thermally upgraded paper is the reference system. You see that you have a difference there in the thermal class of 15 degrees. And depending what kind of paper you choose, you can also get different or a little bit different results. Next slide. So let's assume that we performed an aging test. We invested about 2 years of time. What we get are such curves then. This is an example that we have done about 5 years ago. After determining the end of life of the paper, that was here in this experiment about 54% retained tensile strength. You go into the graph. You have 3 different temperatures, and let's assume you have the highest temperature, which is 155. Then you go to 54%, and you read how much time it needs or required to reach this 54% retained tensile strength. You similarly do it then for 140 degree and 125 degrees. And you use these numbers then, if you go to the next slide, to plot it in a so-called Arrhenius plot. The nice thing is in this Arrhenius plot is that you can extrapolate to longer times or lower temperatures. So what we see here in the Arrhenius plot is on the x-axis we have the temperature, but not only the temperature, it is 1 divided by the temperature in Kelvin. And on the y-axis we have the life, or how long it takes to reach the end of life criteria on a logarithmic scale. We see now again the 3 points that we have taken from the other graph. So we have the 3 different temperatures, 125, 140, and 155. We have the times on the logarithmic scale, and then we can extrapolate to, for example, in this example, it is 150,000 hours, which is equal to about 70 years. And what you can then do, okay, if you click once, I think something will appear, yeah. So you either then can estimate, if you have 2 different curves or straight lines here, you either can calculate the difference in temperature, which is indicated by the arrow now, or if you click again, we get the difference between the 2 materials in lifetime. And as I mentioned before, so a whole aging takes roughly 2 years if everything goes well. Sometimes it even takes more time. And to increase speed in this project, we decided to use as a basic framework for the new product DPE. So we changed it slightly, but we expected no difference in the aging. And to prove that, if you go to the next slide, we did not perform a full aging, but only a part of it. What we want to prove is that we have a thermal class of 130 degrees in mineral oil, potentially 140 in ester liquids. We also want to prove that we have similar mechanical properties like thermally upgraded paper. We do not want to have a material like aramide paper, but more like a TUK, so that we also have the price more in the range of TUK, and it should be based on a cellulose-based material. Results. So the result of this reduced aging test. As I mentioned before, for DPE, we did this 2-year aging test, and in this aging test, we proved that the material has a 10 Kelvin higher thermal class than thermally upgraded craft paper. We did the test according to the IEEE standard C57100. And in this standard, it was a previous standard, an earlier version to the actual standard, where we had a ratio of liquid to solid divided into distribution transformers and power transformers. So we did the whole experiment for the aging according to the ratio for distribution transformers. Yes. What we at the end got, if you go to the next slide, Kevin. Was again a linear slot where for DPE, where we have in the blue line is representing DPE in aging of DPE in mineral oil with a resulting thermal class of 130 degrees C, and in ester oil with a thermal class of 140 degrees C. So we have 10 degrees C higher than for typical thermal upgraded paper. Next slide. IEEE and IEC have design temperature limits for transformers. They are a little bit different from how they come to the system thermal class at the end. But if you look at the very right column in the red table and in the blue table, so these numbers are at the end the same. So when we go to industry proven system for kraft paper and mineral oil, we see that we have a system thermal class of 105 degrees C. If we use thermally upgraded kraft paper and mineral oil, we will get at a thermal class of 120 degrees C. DPE is 10 degrees higher, which is 130 degrees C, and DPE in ester liquids is at the end 140 degrees C thermal class. So finally, we get to the aging curves of the new material that we have developed. What we see here is on the x-axis the aging time in weeks, and on the y-axis the retained tensile strength in percent. We have chosen to use the aging temperature that is in the middle. So usually when you do a full aging, you have 165 degrees, 180 degrees, and 150 degrees. And in the red curve is the aging results of K-buff. Then we have with the black dots, it is TUK, so thermally upgraded kraft paper. And in the light blue, we have the new material, our 130 degree power conductor insulating paper. And what you can see now is that between the K-buff and the TUK, this is a 50 degree difference in temperature class. And there is at least the same difference, maybe a little bit less, but we think that it's at least the 10 degrees that we have already proven in the aging of the DPE. Next slide. This is your slide, Kevin.
Okay. Yeah, thanks, Lars. No, so I'll just come back to explain, Lars showed one of the, a slide with some of the goals of what we were trying to do to develop this, technology for specifically for conductor insulation paper for power transformers. One of the goals was for it to be sustainable. So, this paper is engineered still using 100% cellulose, not 100% kraft, but with 100% cellulose. So what it means is that, you know, these are sustainable, you know, renewable fibers. And so compared to synthetic material options, you know, they're derived from natural plant sources. They're fully recyclable, at least, you know, prior to impregnating with liquids. And even after impregnating with liquids, you know, they can be, you know, downcycled as a fuel source. So when we talk about sustainability, and you know, there's a program for that called Eco Design for Sustainable Products Regulation. So you know, we're hitting a lot of the you know, the points for sustainability. You know, for that example, look at what makes something sustainable. So so this is you know, a sustainable solution in addition to you know, the higher thermal class that Lars talked about in details. So with that actually brings our presentation to a close. Oh, I guess one last slide. So sorry about that. So so just to summarize, so this new paper, we've developed it, and we've also partnered with an OEM to actually look at putting this in transformers. So it's been released, it's been approved. There's the ability to make transformers with this paper. We did achieve all the other properties of TUK paper, thermally upgraded craft paper, with this new paper. So you know, mechanically and from a winding perspective, it behaves similarly. But the advantage there, again, to reiterate, is we have 130 thermal class in mineral oil and 140 in ester liquids. And so again, those higher temperature limits, you know, allow for those higher temperature capabilities allow for higher temperature limits under overload conditions. And so when you can do that, again, you know, specifically transformer purchasers, end users, or utilities, they can update their specifications for transformers to use this paper and ultimately take advantage of the extra capacity allowed through the standards and the increased temperature, you know, allowed from the use of this paper. So and from the OEM side, OEMs can redesign higher overload capable transformers. So so that's possible. And then finally, it is a sustainable material. So it can be, again, it can be completely recycled before liquid impregnated, or it can be downcycled at the end of its life safely. So good. So that's the overview. And now, Frankie, I'll turn the microphone back over to you for our wrap up. Thanks.
No, before the wrap up, Kevin, you have a lot of questions to answer with Lars.
Awesome.
I have to say, out of the many people we have on here, we have a lot of questions. So clearly this topic is something interesting. And first of all, I will say I apologize if we don't get to your question, because we have a stack of them. But I will do my best, and if not, you can, when we send out the wrap email in the next couple of days, you will have access to email addresses where you can fire your questions directly to the experts and get a personal answer. Thanks, Lars and Kevin, for responding to those. So I will kick off with the first question is about pressboard, and I know you touched on this, I think, Kevin, in the presentation, that pressboard is rated to 120 degrees C, but can you just confirm for the sake of the listeners, so that the question is standard pressboard suitable for power transformers with higher operating temperatures of conductors and of insulating liquid? Can you just clarify that for our listeners?
Sure. Yeah. So yes, the answer is yes. You know, so again, the technology that we use to develop this as a power transformer conductor insulation paper, again, is based on, you know, the similar technology of previous distribution transformer layer winding insulation paper called DPE, as Lars talked about. So to achieve those higher temperatures, there's no need for a different press board material. So in distribution transformers designed with DPE and to take advantage of the higher temperature capability, standard press board can be used in the 130 thermal class, and all the temperature limits that were shown in the charts can be achieved with standard press board. And I'll touch on that paper. So I referenced a technical paper that we wrote on the subject, and it shows that, you know, the same material can have different thermal classes depending upon which system it's in. So standard press board with non-thermally upgraded paper and mineral oil actually has a lower thermal class than the same same cellulose press board in the system with thermally upgraded craft and mineral oil. So yes, there's no need for a different press board in order to take advantage of the temperatures that we mentioned with this new paper.
Okay, thank you. And whoever wants to answer this, feel free, Lars, Kevin. But one quick question along the same lines. So the question is, if we specify 130-degree paper in our transformer, the understanding is that it's still only tested to the regular temperature rise tests. And the question is, are there other components in the transformer that could be a bottleneck to achieving this higher thermal rating?
I can try to take that one, Lars, or go ahead.
Yeah, I mean, the standard, we're still according to somehow to the standard, at least as Kevin mentioned, it is this semi-hybrid mix insulation, let's say. So it is not really something extremely new according to the system. It's new for the insulation that we have insulation temperature clause, but the system is not really new, and it is. I think it's also used, Kevin. Aramide papers are used in this for doing it right now, but of course, with the new solution that we have, that's much cheaper, because when we look at price for, I mean, we'll put out the number, an exact number, but that's maybe, I would expect it's a difference in factor of 20 between aramide and the standard paper, 10 to 20. So yeah, that's I think the new thing.
Yeah, and of course, Lars, just to confirm, it's a different application. I mean, there are certainly many customers with Weidmann that utilize aramid paper because the application requires that significantly higher temperature rating. We're talking here about a different application within the general power transformer world. A question we had: do we have any empirical relation to provide on how the insulation degrades over time, or if we can use an increased thermal life in our loading calculations? So more than, I guess, the standard 20 years used in loss of life calculations. Can we change anything there?
Yeah, I guess I can take that one. So you know, the extra 10 degrees of thermal class in mineral oil, or 20 degrees of this new paper in esters. So there's really two options. So you can either have a longer life at similar temperatures, or you can have higher temperatures with a same lifetime. So, you know, the higher temperatures with the same lifetime is that overload capability that we talked about, and longer life at the same temperatures is the other option. And just to kind of ballpark what that equates to, I mean, 10 degrees in practical terms, you could say, is about double the life. So So anyways, hopefully that answers the question about how that 10 degrees can be applied either for longer life or for higher temperatures, you know, at a similar life.
Yep. Another question relating to FR3, is the material, or have we done testing to validate the material's compatibility with FR3? Obviously, Nomex, we have no issue at all with, or Aramid products with FR3. Is it the same here, and have we got test data?
Since it is based on DP or based on a cellulosic material, which is widely used, or all these materials are widely used also already with FR3, but also with other esters. I mean, it's a brand name, FR3. So that's the natural esters, but also synthetic esters. And we don't expect any negative impact of these esters on our product or on the aging.
Okay. And a question here, why would the expected thermal class for this material impregnated in ester liquid be 140? Is that not already the thermal class of TUK impregnated with ester, according to IEC 60076-14 Annex C?
Yeah, no, that's a great question. I'll take that one. So, yes, no, we're aware of that, and actually in you know, the IEEE community, there was a reference to that, an older reference to that, you know, which the IEEE community is in the process of clarifying that. As we speak, we have an update to a guide that I'm a part of a working group. I'm the chair of a working group to work on that, and actually TUK and esters is more around 130. So this paper in esters is 10 degrees higher than TUK in esters.
Okay, thank you. Another question, is there any variation for electric field capability for 130 material, either a benefit, enhancement, or weakness?
Let me take that one. You got it, Lars?
Yeah, sure. No, I don't get it.
What's that?
Yeah, take it.
Yeah. No, you know, we touched on it, but just to expand a little bit about when we developed this paper, it's not just the thermal class studies. Okay, so this is still 100% cellulose product, and we have completed, you know, all of the other physical, mechanical, and electrical testing. So there's no change in any other aspect of design, meaning like mechanical considerations or electrical dielectric considerations with using this paper. There's no other electrical mechanical design changes needed because you know, we've tested and proved that this paper is practically equivalent to the standard 100% craft papers or thermally upgraded craft papers.
Okay, good. And along the same lines, Kevin, I assume we had a question about DGA diagnostics criteria, that remains also the same as craft and TUK papers.
Yeah. Again, you know, the technology that we're using here is not some brand new synthetic or something unknown, some completely different molecule. You know, we've been able to design this paper, you know, with some different kinds of celluloses can be sourced from many different ways, and we've found some more thermally stable versions of it. So yes, so DGA would be expected to be very, very similar to any other cellulose paper or board product, actually.
Yep. And sorry, I think you may have covered this in the last one, but I'll double check. What is the dielectric withstand of this 130°C paper in comparison to conventional thermally upgraded or craft paper?
Yeah, in terms of things like dielectric constant dissipation factor, you know, AC breakdown, impulse breakdown, it's identical, practically identical to other cellulose papers, craft papers. There's no there's no there's no differences that would require any kind of changes, you know, from a base material property.
Okay, good. Quick question on supply, actually. Do we have any indication yet on what thicknesses would be available? Will it be the same as our TUK offering or craft paper from a thickness standpoint?
Yeah, that's the plan. So we're going to supply a very similar product because it's really the idea to one-to-one exchange what we have right now for conductor insulation. So similar thicknesses, I would really say.
Okay. Yeah, thank you.
Yeah, I'll just add,
yeah.
Frank, if I could, I'll just add. So, you know, so wire wrapping papers are just generally a lot thinner, relatively speaking, compared to, you know, the DPE distribution transformer paper. This DPE distribution transformer layer insulation is offered in a much wider, you know, spectrum of thicknesses. Whereas wire wrap paper is typically on the thinner thickness side. And I'll also add, you know, that just as we have calendared crepe papers, you know, for our craft papers, you know, we could and hope to also have a calendared crepe version of this paper as well. So that's also, you know, in our thinking in order to make, you know, our offering of this new material to have both a flat and a calendared crepe version is possible also.
Yep. Okay, good. Thank you. A couple of questions that I'll just try to address, and Lars, Kevin, brace yourself in case I say something wrong, and
go for it.
Incorrect. But we had a few questions like, is there an alternative material to paper with better insulating performance together with oil? I think, you know, we can certainly talk to you about the options. We've mentioned Nomex, which is a material, an aramid-based material that we've worked with for a long time and continue to work with, that has certainly superior performance characteristics to any cellulose material. So we'd be happy to send you specifications on the comparisons and so on with that. We had a couple of questions from some friends about whether it contains aramid. I think we've addressed that it is not a hybrid product. It's something that slots in below our aramid-based materials that we supply, the Nomex materials. So no, it's full cellulose-based material. Those people that's asking about cost, you will need to contact those lovely account managers from Weidmann about that topic. This product is currently in the final stages of commercial release. So right now we don't have full commercial material rolling, but that is in the pipeline right now. So if you would like price information, I can't share it here because it completely depends on what your requirements are. So please contact your account manager for that. We asked somebody if we had a name for the product yet. No, we don't. It's a good question. So we will be coming back to you when it's available for full commercial release to give you information on that. The next question that keeps popping up is which OEMs are using this, which wire wrappers are using this. Obviously, we can't tell you right now which materials go into which OEMs. I can tell you that some of the largest OEMs in the world have been part of this program to support us in validating and testing. And I'm sure some of that information, if you speak to Kevin, Lars, or your account manager, can be clarified so that you have an understanding of what the level of testing and part of the development program was. To those asking, can you have the presentation? Yes, you can have the presentation, not a problem. It will be coming out to you as always in the next 24, 48 hours via email. You'll have a link to rewatch Kevin and Lars and also the slides. The question from Tom Prevo. Thank you, Thomas. Good to see you're enjoying retirement, but still joining us. Why don't I need a higher temperature spacer material? Because Kevin said so. And finally, I have one question that's just come in. For distribution transformers, are there any concerns about CSA UA approval? Is this obtained already? What approvals do we need for this application, given that it's looking more at power transformers? And have we already addressed that in the development stage?
Yeah. Well, I mean, UL certification, for example, is not really typical for liquid filled transformers. You know, that's more of a thing in the dry type transformer world. So, but yes, this, you know, new material, again, you know, there are both IEC and IEEE standards for the use of high temperature insulation materials, and this new product is meeting both of those standards. IEEE even has additionally, in addition to a standard, it has a guide about the application of high temperature insulation materials too. So this paper is going to be you know, fully compliant with those both IEC and IEEE standards for high temperature materials.
Okay, thank you. And final question, because we need to get all our people to the next meetings or home if you're in a different part of the world. Final question, and I don't want to go into a big DP discussion here, but what is the expected DP of the new paper? Would it be similar to our existing papers, I guess is the short answer.
Very boring short answer, yes.
Okay. Perfect. Thank you very much. Well, we're going to leave it there because we only have 2 minutes left to get everybody out into the next meetings and to everywhere else. I would like to thank everybody for joining. Sorry if we didn't get to your question. I know they're still coming in, but feel free to contact Lars or Kevin or your account manager for further information. Again, thank you very much. We're really pleased that so many joined for this introduction of a new material. We are in the process of continuing to commercialize it very shortly. So for those who are interested in names, pricing, availability, thicknesses, you can always speak to your Weidmann contact or reach out to me. If you don't know who your Weidmann contact is, I will put you in touch with them. So thank you very much, Lars and Kevin, for sharing with us today this presentation. Thank you to our hundreds of people who were on the call today, on the webinar, and we look forward to seeing you probably in a couple of months' time with the next of our 2026 webinar series. So thank you very much. Enjoy whatever remains of your day, wherever you are in the world, and we will see you all next time. Thanks very much.
Thanks, everybody. Thank you.
Thank you.